Hello everyone, I'm Carl Zielinski and today we're gonna talk about arrays in Odin. We will go over fixed arrays, dynamic arrays, slices and enumerated arrays. And throughout all this we will both talk about some basics but also about where the memory actually lives and how copying works and interesting stuff like that. So let's start with fixed arrays. Now fixed arrays are, as the name hints, of a fixed size. They cannot grow or shrink or anything like that. And you create a fixed array like this. You say some ints is 7 integers. So this is a fixed array of size 7 that stores integers. Then you can set values within this array by using this index like this. So you say some ints 3 is 500, some ints at index 4 is 200. Then you can clear the whole array by just putting 2 empty braces like this. This will clear everything to 0 within it. And then you can assign the whole array also like this. And what you should notice here that since some ints is 7 long, we must supply all 7 values here. And then you can loop over the whole array or iterate it by saying for v in some ints, and then v is each element. The loop goes through the whole list like this. And if you want the index at during each loop lap, then you can add in comma I here, and then the I will be the index of that element, which can be useful. And if you want to make it possible to modify values during the loop laps, then you can add in this ampersand in front of v here. So then you can, for example, like in this case, I multiply each item by 2. And putting in this ampersand turns v from an r value into an l value, essentially meaning that it becomes modifiable and addressable by the compiler so that you can change it. Now, where is the memory and how does copying work of fixed arrays? So when you type something like this, array is 3 F32s, and we have the values 1, 2, and 3. And then we make a copy of that array by saying array2 colon equals array, and then we set the first item in array 2 to 10. After this point, the first item of array is still 1, but the first item of array 2 is 10. This might not seem surprising, but what this shows is that there is no shared memory between fixed arrays. When you type something like this, you get a complete copy of it and you can do whatever you want with it. Another way of seeing this is that if you have a struct like this called myStruct, and it has an array of 10 I32, and I32 is 4 bytes big, and you have 10 of them, then this struct will be 40 bytes big. And if you make the array bigger by typing 20 here instead, then this struct will now be 80 bytes big. So this just shows again that the memory of this array exists within the variable, or in this case, struct field itself. There is no sort of separation of it. So let's look at something nice about fixed arrays, which is array programming. So imagine we have a fixed array of 3 F32s called position, and this one will be all zeros because you don't supply a value for it, so it will be 3 zeros. And then we have velocity here, which we say is a fixed array of 3 F32s, and it has the values 1, 0, 2 of the 3 elements. Then we also have a F32 variable here called delta time, and it has the value 0.016. Now what you can do is that you can say position plus equals velocity times delta time. What this will do, it will take the velocity and multiply each field by this delta time, and then it will add it to the position. So position is now 0.016 because 1 times this, and then there's a 0, so there's 0 times this, and then there's 2 times this, which is 0.042. What this means is that whenever you have 2 fixed arrays where the type of the element is the same and they are of the same length, then you can do these math operations on them. So you can add them, and you can also multiply them by single numbers like this F32 here. And what this means is that, I make video games, and in video games you have lots of these vectors where you want to do vector math, adding vectors together and stuff. And in my code, and in most people that do Odin programming for games, a vector in 3 dimensions will just be a type alias of 3 F32s. In many languages, you would have some kind of operator overloading or something to supply this addition and multiplication. In Odin, there is no operator overloading, but the primary use case people usually have for operator overloading is to implement these math operations for vector math and stuff. But you do not need that here because it just works out of the box. Another nice thing about this is that if 2 libraries both use this kind of thing for the vector, then you have the vector math working between the data that those 2 libraries use. They don't have, like in other languages, maybe one library has one implementation of vector 3, another has another one, and you can't add them in a nice way because they are incompatible. Here you just have some very basic type that is a fixed array, and you can just add them and stuff however you like. Okay, so let's move on to talking about dynamic arrays. Dynamic arrays are, as the name suggests, possible to grow and shrink as your program runs. So you would create a dynamic array like this. You say this variable is called dinar, and it is a dynamic array of integers. I'm not saying how many here or anything because it can grow, so we don't need to say that. And then to add an element to this one, you write append, and then you send in the pointer to the dynamic array, and you add the number 5 to it. So now the first element of the dynamic array has value 5. There are 2 ways to remove from a dynamic array. Either you use unordered remove or ordered remove. Unordered remove is a bit faster, but it can change the order of things. So what it does is, if you have a dynamic array of 10 things and you do unordered remove of something in the middle, then it copies the last one to the middle and then makes it one shorter. While ordered remove removes the one you want and then copies everything back a step so that the order is still kept the same. So whenever you can, use unordered remove because it's faster, but if the order matters, then you use this one. Just like before, you can iterate dynamic arrays with the 4 value comma index in dinar, just like with the fixed array. And if you want to be able to modify the value during the loop, then you just type the ampersand in front of the value again. So let's now talk a bit about what does append actually do. So when you have something like this, where you declare a dynamic array of integers and then you add 5 to it, then what happens, and sort of what happens under the hood? This variable dinar is just declared. There is no value given to it. And just like with all variables in Odin, when you just declare something, all the memory for it will be all zeros. So if you make an integer and you don't supply a value, then the integer will be 0. And in this case, this whole dynamic array thingy here will be all zeros. But what does that actually mean? Well, the internal structure of a dynamic array is something like this. You can see it as a struct that has a field data, that is a raw pointer, and a field length, that's an integer, and a capacity, that's an integer, and an allocator, which is a whole other struct that lives within it. And all this is, when you type like this, all zeroed out. So when append comes here and wants to append 5 to this dynamic array, then it looks at it and it notices that everything in here is 0. The data is 0 and the capacity is 0. So it knows that it needs to initially at least allocate some memory for this dynamic array. So what it will do in that case is that it will just look at how big the integer is, and then it will allocate some initial amount of memory. I think maybe it's like 8 slots or something. So there's room for 8 integers in this dynamic array. Let's say it's 8. I don't remember exactly. But in order to allocate this memory, it needs an allocator. So then it checks the allocator field, but that allocator struct is all zeroed out. So then it needs to fall back onto something else. And everywhere in Odin, there's a context pass around implicitly, and there's a default allocator on the context. So since this allocator is all zeros, then it will go ahead and use the context.allocator here instead, and it will allocate room for 8 integers using that allocator, and it will store the pointer to that allocation in data. It will also store the allocator in the allocator field, so that future appends will use the same allocator, and if you later destroy the dynamic array, it will use the same allocator to destroy it. And then the capacity, of course, it will record, maybe as 8 in this case, and then it will, at the correct position in this memory, it will write your number 5, and then it will increase the length by 1. So that's what happens under the hood when you run append. Then the question is, when does it grow? Well, it grows when the capacity is equals to the length. So if it tries to add more things here and say the capacity is 8, but the length is 8, then it's like, oh, we need more memory. Then it will do the same thing again. It looks at the allocator and it allocates a bigger capacity. Maybe it takes the current capacity times 2. I don't remember exactly what it does. So maybe then it has room for 16 things instead. And it will then take the old memory and copy that whole memory into the new memory just allocated. So the whole memory of the array sort of moves to a new place in memory. You can't assume that it will always be at the same place due to reallocations like this. And when it has done that, then it can set the memory, the new data pointer here, and set the capacity to 16 and write the new thing in. And it also deallocates the memory for the old data block for you, so that you don't need to do anything manually when append grows the dynamic array. So let's say you want to make append use some other allocator. Then there's a couple of different ways to do that. Here's one. We still declare the dynamic arrays like this. This is all zeroed out. All these are 0. Then we go and explicitly set the allocator field of the dynamic array to context.temp allocator, and then we add 5 to it. Now, when this grows the first time, it will try to use the allocator on there, and since I set it to something, it will use that one, and it will allocate using that allocator. And I have a whole video on allocators and temp allocators, but the temp allocator is good for when you don't care about the allocation in the long run. It's something you can clear every now and then and just have all that memory just go away. Another way is to declare it like this, but instead of setting the allocator on the dynamic array, we set it on the context, and then we call append. Now, since the context is implicitly passed to everything, to every call procedure, then since this will be 0, then it will go and look at the context of the allocator instead, and then it will pick it up that way. Another way is to say that dynamic array :equals make dynamic array of integers, and then you provide the allocator like this. Of these three, I would say either do this one or this one. Modifying the context.allocator is more error prone, I would say, since the change to the context.allocator lives on through until the end of the current scope. So it's better to do this, but I think the best thing is to sort of make it like this. And this doesn't allocate any memory until you run append. It just sort of does the exact same thing as this. Also, one thing to notice here is that in this case, I set the allocator. You actually can't access these fields in here. If you want the length of the dynamic array, then you type len dyn ar or cap dyn ar. And this len dyn ar works also on fixed arrays and stuff like that. So it's an exception that you can modify or access the allocator field on the dynamic array directly. You can't do it for the other internal fields of it. And of course, to make this actually equivalent to these two, you would have a append here as well, of course. But point being that in all these cases, it will use the temp allocator when it needs to grow it. You can also pre-allocate dynamic arrays. So make has some additional variants. This one, where you supply a number here, sets the capacity and the length to 10. So it will be sort of pre-filled with 10 zeroed out integers. And if you supply two numbers here, then you will get the length is this one and the capacity is this one. And I don't know why this comment is here. And as for copying, we looked at fixed arrays, and fixed arrays copy, you know, when you assign a fixed array to a variable, the whole data comes over and all that. And that does not happen with dynamic arrays, because if you have a dynamic array like this, a dynamic array of integers, and then you append 5 to it, and then you create a new one by just copying it like this. Then you can go back and look at the raw dynamic array struct up here, and what it does, it sort of copies this whole thing, and what you can see here is that it copies, it copies the length and the capacity and the allocator, but this is just a pointer. So that just points to some other memories. So these two dynamic arrays are actually still sharing the same data pointer. And when they are still sharing the same data pointer, then things can go wrong. That's why it says don't do this here. Because if you appended 5 here and you then copied it, and then you go and append, you make a loop and you append 7 64 times to the dynamic array. Remember the capacity initially, maybe it's 8 or something. When it goes over 8, then it will grow, but only this one will grow, since they have their own separate copy of this pointer data inside them. Only this one will grow. So then when it grows, it will deallocate the data pointer. So then this one suddenly has a data pointer that just points to garbage. It's deallocated. So this is a setup for crashing. That's why you do not do this. If you want a clone of a dynamic array, then what you can do is you can type dynamic array 2 : equals slice dot clone to dynamic, and then you write dynamic array : like with these brackets, and we'll talk about this slice syntax soon, but this is just to show you how to do it properly. And then you can also pass in some allocator if you want to, or just use context allocator by default. This will give you a complete clone of this dynamic array using some allocator. And then it will have its own data field inside there, and that's the key thing here, right? And then we can look at destroying and clearing dynamic arrays. When you want to destroy a dynamic array, that means free all the memory associated with it, then you run delete and you put in the name of the dynamic array like this. And when you want to clear it, you write clear and the dynamic array with an ampersand like this. And here you can see that this one will be a pointer so that it can modify the fields of the dynamic array itself, and this one is not. Why does this one need to be a pointer and this one not? Well, if we look again at the internal dynamic array, the raw dynamic array, then when it wants to delete it, then it just needs to use the memory allocator here and go and say delete the data. It doesn't actually modify any field within the struct. It just takes the pointer data and then tells the operating system to, hey, go free this memory. Doesn't do anything. It doesn't modify this at all. That's why delete does not need a pointer. However, clear needs a pointer, because what clear does not delete any data, does no deallocations. It's just for resetting the whole dynamic array. It will just set the length to 0 and the capacity will remain. So when any capacity you have sort of accumulated by doing lots of appends or something to it will still be there. So let's now talk a bit about slices. And slices you can think of as a window into an array, for sort of looking into a section of an array. And you create a slice by doing something like this. So here I have a fixed array of 7 elements again. And this is just a fixed array, but if I want to create a slice that looks into a part of this fixed array, then I can say some ints and then these brackets, and then I say I want the slice to go from index 2 to 5. Now this int thing is 3 elements long and it contains 72, 12 and 3, because the second element is 0, 1, 2, 72, and then it takes the second one, third one and the fourth one. It does not take the fifth one. This range is sort of exclusive, so it will have all the elements from the second index up to the fourth index. So it's like, so this range here is the 5 is excluding the element itself. And if you can also do stuff like this where you exclude one of the indices or both of them. So in this case, this slice will look at, it will go from the first element up to the last one. So it will just take these 6 things here. So it will contain these things. Similarly, you could do skip the first index, then it would go up to, it would contain these 4 things here if you wrote 5 like this. And finally, you can also just write colon with no indices at all. Then it will make a slice that looks at the whole thing. And the key difference here is that you sort of the type of the thing changes. So if you have int colon equals some ints, then the type of this thing is fixed array of 7, but the type of ints is just slice of int. This is, whenever you see just empty bracket like this, then it is a slice. So I said at the start here that a slice is sort of a window into an array. What this means is that a slice is just a pointer and a length. Internally, a slice is, you can think of it as a struct that has a data field and a length. So when you write something like this up here, for example, then we look into this fixed array and we fetch a pointer that points to the second element, 0, 1, 2. So we fetch a pointer that points here, and then we say that we want 3 items. So the slice in that case, the data pointer points to the element at index 2, and then the length is 3. That's all it is. And something to notice here is that there is no allocation when slicing. Whatever the memory of the thing that you're slicing comes from or is, you're sharing that memory. So if you for example slice a dynamic array and then you destroy the dynamic array, or if you slice a fixed array and then that fixed array maybe goes out of scope or something, then your slice is pointing to invalid memory. So you need to think of that. It does no allocation when slicing, but that's a good thing, because these slices then become very lightweight and you can use them in lots of situations without worrying. So since these slices are so lightweight and don't do any allocations and stuff, then you can have sort of, I have sort of the recommendation to prefer to pass slices. And preferring to pass slices just means that whenever you want to pass an array, a number of things, then you make sure that that parameter in that procedure is a slice. So you write something like this. This is a slice of integers here. When you have it like this, then you can use this procedure with a dynamic array. You can slice the whole dynamic array, does no allocation. You just get a window into the whole dynamic array. You throw that in there. You can also take some fixed array and slice the whole thing, and then you can use it. So it becomes like a nice way to make arrays of different kinds more usable, because they can all be sliced. Now, I say that slicing, when you write something like this, it does not allocate any memory, but you can make slices that have their own memory. This is 2 different statements. Slicing does not allocate memory, but you can create a slice where the data field inside is not owned by something else. It is only used by the slice. So there's a couple of different ways we can make a slice have its own memory. In this case, for example, I have a fixed array of 128 integers, and then I fetch the first 20 integers from there like this. Then I can say slice.clone. This is a package. This is core:/slice package. You have to import that. So I say first 20 clone is slice.clone first 20. What this does is that it will make a new slice, but the data field inside the slice will be separately allocated to be as big as the slice that we fed into it, and then we'll copy over the data so it has its own data. It's not dependent on wherever the memory of the original slice came from, which in this case is this my numbers fixed array. You can also, as usual, feed in a custom allocator to slice.clone if you wish to. We can also explicitly make slices. The difference is up here we already had a slice to clone, but if we don't have one to clone, we just want to make one, but we want to make it so that it has its own memory. Then we can use make like this, and we just say brackets integer 128. Then you have a slice of 128 integers where the slice itself owns the memory. And you can, as usual, feed in a custom allocator here. Now, if you have done any of this where you've made a slice have its own memory, then you are in charge of making sure that that memory is deallocated. So you can run delete and feed in a slice like this, and you can also run delete and feed in a slice and then an allocator. if you remember the dynamic array, we used to say delete, and the dynamic array remembers itself which allocator that was used to allocate it. And it needs to remember that, because then, you know, if when you run append and stuff, it will reuse the same allocator. But since a slice is just allocated once and then at some point deleted, it does not need, there's not such as a big need to contain the allocator within it. So the slice does not actually remember which allocator was used to create it. And you can see that in the raw slice here. There is just a data field and a len field. There's no allocator field in there. So with that in mind, if you run delete like this, you just feed in the slice, then it will use, that implicitly uses context.allocator. But if you use some custom allocator to make it or clone it, then you need to feed that in here. Of course, if you use the temp allocator, then you don't need to do any of this, because temp allocator implies that you will run instead free all context.temp allocator at some point in your program, which will at that point make everything that's on the temp allocator invalid, so that you don't have to worry about it. So let's now just quickly go through a nice little special kind of fixed array called enumerated arrays. So you can have enums in Odin, right? So you have nice people here, which has 3 different enum values. Then you can take the enum and, you know, when you make a fixed array, then you would type 7 here to make 7 integers. But instead you can just put the type name of an enum. So this is a enumerated array where the sort of the indices use this enum, and it has some nice syntax going on. When you initialize this nice rating here, you map nice people to an integer, and this integer is sort of a score of how nice they are. Then you just use the enum names here like this, and then you say a number. And then later you can fetch one of these people's nice rating by just indexing it, but instead of indexing with a number, you just directly use the enum value. You can also do sort of a partial initialization of the enumerated array. We can look at this one down here first. In this case, we are just making an enumerated array that's all zeros, but it will still be as long as there are a number of elements in this enum. So it's, you can again think of it as a fixed array, that it, even though you don't supply the initializer like this, it will still be as long as this enum, so that you can later expect it to have that many elements, so that you can use this enum indexing thingy. And then you can also do something like this, where you put #partial in front of the type name, and in that case you only need to mention some of the enum values in there and the value you want for that one. It will still make the array as long as there are values in the enum, but all the other ones associated with the other enum names will be 0. Other than that, this enumerated array works just like fixed arrays. The enumerated array itself owns its own memory. There's no dynamic allocation involved when you do things like this. And if you make a copy of a variable that is an enumerated array, then you get a copy that has all its own memory. Okay, that's it for today. But before we end, I'd just like to say I am working on an Odin book that will hopefully come out sometime soon. The initial version of this book will be sort of web-based, but it will be a book for sort of learning and understanding the fundamentals of the Odin programming language, and maybe sort of trying to bridge the gap between online documentation and years of experience of using this language. And the stuff we saw in this talk here today is sort of a talky version of one of the chapters in the book, actually. A big thanks to all my patrons who donate money monthly so that I can continue making these videos, and those patrons are these people. And I want to do a extra shout out to my super supporters who donate $20 a month, and they are Cody Green, Ian Seckington, Mihails Mozajevs, and Radek Micek. And if you want to support me, then you can become a patron. There's a link in the description, or you can use the super thanks button below this video to leave a single time tip. Thank you so much for watching. Happy programming. Bye bye.